We are back once again. This is day 42 of LeetCode every day. 42 days of problem solving carnage. We're in the trenches every day, scooping out logic, building logical structures that make sense, solving problems. Bit of a shorter session today, but trust me, a longer session overall. Did like 4 or 5 hours after work, so this would actually be the 5th hour so far. So this would be the 5th hour. We're just going to do new problems. Same problem we were stuck on yesterday, which was graph valid tree, which is actually a little bit nutty because this problem that we were working on was supposed to be able to allow us to use the union find data structure, which we can use, but we had a problem with actually how we traverse graphs, which we didn't know how to fix. Now we actually know how to fix. It's actually a common problem for graph traversals. So we should be able to solve this problem today, hopefully, but that's besides the point. Yesterday we made a video called Union Find is Not Balanced, and literally the first hour and a half, the entire hour and a half of the video is just us getting fried by Union Find. So don't understand it completely yet. Did it a few more times. We can now pull the data structure out of our brain and lay it onto the page at will. That's a good sign. So we've internalized the code. Now we need to internalize the intuition. So we have graph valid tree do, number of connected components, and then the earliest moment when everyone became friends afterwards. So that being said, the graphs galore continues. Reflections so far, yeah, we did union find yesterday. We seem to have understood the data structure. Now we just need to learn the intuitions of how to use it, how you can play around with it, how you can mess around with it, right? How to extract the points that we're looking for from the union find data structure. That being said, though, progress is being made at a steady pace. So even if things don't go well, progress is being made, so we'll get where we're going eventually. So hopefully by the end of August, unlikely by the end of August, this pace is not sustainable. So probably by the end of August, we'll definitely have finished the 75 problems in the grind 75, but ideally I'd like to have all 150 done, which would be pretty epic. Now it'd give us a good grasp over everything, and then we just do review, right, and try to get optimal time, right? So the other thing that we have, right, so we're also I'm noticing a lack of ability to actually do dynamic programming problems. And I think it's because we're actually lacking in the supplemental reading section. So we probably need to do more supplemental reading, right? Because we're intuiting all the things we need to actually be able to learn application, right? But the problem is, why take the time to slowly intuit something, right? When the pattern is already secretly there. When you read it, right, if you're already having enough application, reading actually speeds up the process, because the moment where you have that light bulb is expedited just by reading the content. So then once we do that, it'll be much easier to pull the gemstones out of applications. So yeah, so we need some supplemental reading. I've received a recommendation from the Copy Ninja about the algorithm design manual. So thinking about copying and reading that. And when I say copying, I mean going to libgen.ri or si or the 50 domains they have for that website, right? And looking and I mean acquiring it legally, right, through Amazon or a other respectable source, not through libgen. But yeah, other things, we're weak on DP. We're fixing our graph struggles now. I think we're relatively okay on trees, especially now that we know different ways to visualize it, right? And yeah, so I think that'll be the goal for today's session, right? To fry this problem that fried us yesterday. I also learned, I think another way that's good for practice is to get blocked. So we're blocked by this problem, but ultimately the struggle for this problem elaborately will encode the solution for us once we finally figure it out. If we look at the solution without struggling enough, and the struggle is going to be relative here, then we actually don't learn too much. It's just easy to remember when you struggle and then get it in. So I think we should be able to solve this one. We know why we couldn't solve it last time. So we should be able to this time, and feeling confident about that. And then from there, we'll try another problem if we can get there. So yes, make sure to join the Hyperbolic Coding Chamber Discord. We have thousands of people joining every single day talking about their secret cheat codes. Also, the people who are interviewing everyone are actually in the Discord giving people the interview problems they're going to get. So you might as well join and, you know, get in there with your interviewer. You maybe drop a blank check. But this would be day 42 of the grind, 75, or just LeetCode in general, right? The goal would be to finish all the problems, and then maybe we'll try our hands at code forces. That sounds pretty cool. But that being said, we'll start the timer. So we're back. Okay, so you have a graph of n nodes labeled from 0 to n minus 1. You are given an integer n and a list of edges, where edges sub I equals a sub I, b sub I, indicates that there is an undirected edge between nodes a sub I and b sub I in the graph. Return true if the edges of the given graph make up a valid tree. So the question is basically, is the graph a valid tree? Well, we know that a graph is a tree. I mean, a tree is a graph, right? It's just a graph, right, where every node is connected, right? So every node can be reached from the root node, right? Or a path exists between, a node can be reached from any other node. Not any other node, but their path exists to a particular node, right? And, right, there are no cycles, right? And so for this one, we can see that that is actually true, right? Every node is connected, right? And there are no cycles. Now we don't want full connection. A full connection, we're fully connected, which would mean any node is reachable by any node. That would actually give us a cycle. But here, right, every node is connected. Every node is connected, but there is a cycle, so we actually have to return false. There's actually two things we need to check here, right? There are no cycles and graph where every node is connected. So if we want to use union find with this, union find actually will not help us in the sense of knowing if there are or aren't cycles, but it will help us know if every node is connected. Right? And another way we could know if every node is connected, right, we could do a DFS, right, just to generate some possible solutions, right, in terms of how we know everything is connected. We do a DFS, right, and we'll just say do union find, which will help us know if every node is connected, right? And then we could also do a DFS, right, where we check, we try to find every node we can, right? Try to find every node we can based on the edges, right? Based on edges, right? And we could add it to a map, right? And if map dot size does not equal n, then every node is not connected. But I'm not exactly sure how we would go about doing a depth first search based on this edges matrix. So it seems easier to use union find for this, checking if every node is connected, right? And then we can do a DFS to figure out if there are no cycles. So the first thing we want to do, right, let's implement, right, checking if there are any cycles, right? So how could we check if there aren't any cycles? To do this, what we could do is to create a new way to visualize our graph. Since we have these edges, right, we want to turn these edges into an adjacency list. So if we turn these edges matrix into an adjacency list, then from here, right, we'll be able to check if there are any cycles by doing a depth first search through the adjacency list, right? So the first thing we need to do is do edges to an adjacency list, right? Then we could depth first search through the adjacency list, right? And if we visit a node twice, right, avoiding simple cycles, right, then we have a cycle, right? So let's actually do that, right? So we want to transform our edges to an adjacency list. So we have n nodes, right? So we have n nodes labeled from 0 to n, which means that the nodes that we actually have, right, are going to be 0 to n minus 1. So if that's the case, then we can actually do adjacency list to start, right? We're going to have a map of number, right, to an array of numbers, which would be the nodes that we have connections to. And then from here, I'll make this bigger. And we're going to say let I is equal to 0, while I is less than n, right? I plus plus. We're going to say adjacency list dot set I equal to an empty array. So we're just going to set it up to be empty, right? And start it with our vertices. Right. The other thing we're going to need to know is that these n labeled nodes are distinct. Given an integer list n, a list of edges where edges sub I. Okay, so there's an undirected edge between nodes AI and BI. So we'll just assume that the list of n nodes is distinct, right? Because we know we have nodes 0 through n minus 1, but the actual edges, right, maybe, right, we're just assuming that for input validation, the edges in the edges array only include nodes in between 0 and n minus 1. So we'll have the start of our adjacency list, which will look something like 1 mapping to empty array, right? At least for our start example, we'll have 0 to 4, right? So I have 4 more of these. I'll have 0, 2, 3, 4, right? So we want to get the connections into here, right? And so we're gonna want to iterate over our edges. We're gonna say const edge of edges, right? Or we want to create a connection, right? But we're gonna have to create, since it's undirected edges, we're gonna have to create a bidirectional connection, right, between 0 and 1 and 1 and 0, right? But when we do our depth first search through, we're going to want to ignore these simple cycles. So we'll say map.set edge sub 0, right, edge sub 1, and then we'll do map.set edge sub 1 to edge sub 0. Now this is going to allow us to create that mapping, right? And just to start and make sure that we're on the right track, our value is actually not named map. It is named adjacency, or adjacency list. We want to print that, and we're just going to return true to start, but we just want to check if our adjacency list values make sense. Right, and what we're going to actually want to do, right, so we can't set it equal to a singular value because what's in the map is actually an array. So do adjacency list dot get that array, and then we'll push a connection to it, right? We'll do the same for edge 1, right? We'll push connection to edge 0. All right, so let's check our map. 0 has a connection to 1, 2, and 3. 1 has a connection to 4, 2 to 0, 3 to 0, and 4 to 1. So that looks perfect so far. All right, so now we have our adjacency list. Right, we want to check if there are cycles. Right? And so we want to do a depth first search to make sure that there are no cycles, avoiding simple cycles. right? What we could do right is visit every node, and then as we're visiting, really we'll iterate through the adjacency list, right, for a key, and then we'll iterate through all the neighbors. As we visit each neighbor, right, we'll look through that node and remove the node if it exists, right, in its array. So we'll visit one, right, and to make sure that we don't actually trigger a simple cycle, right, we'll look up one, which is its neighbor, and remove 0, right? And so this way, you can say for const key and neighbors of adjacency list, right, now we can check if there is a cycle, right? And then we'll say const visited, which is going to be a new set, right, of numbers, and we're going to say, right, if visited, right, doesn't have the key, then that's perfect, right, which means we haven't visited it before, right? What we want to do is do adjacency list. What we want to do is add it to visited.add key, right? And then we want to prevent simple cycle, right? But we also want to visit its neighbors. Right, so we could say we added 1, 2, and 3, right, to the visited array, and then we go to 1 and we'll say, okay, we'll visit 4. And then we'll go to 2 and we'll say, okay, it would have no neighbors, right, because we would remove 0 from 1, 2, and 3. 4, right, we'd go to 4 and we would just visit 1, right, because we actually wouldn't visit anything because we would have removed 0, would have removed 1 from both 0's list and 4's list. This actually could work. So we'll say neighbors dot for each n, right? I'm going to want to say, keep alt tabbing by mistake, if visited, right, does not have the neighbors for n, right, we want to do visited dot add n. Right, and then here we want to prevent simple cycles, right? And so since we're visiting the neighbors of the key, we want to remove key for every neighbor. All right, so we're going to get the array, right? We're going to say map, or not map, adjacency list dot get, right, the array for n. We're going to say r equals r.filter, and we're going to filter out the value. And we could actually set this to a map so we could check or remove in constant time. But we're going to say filter, right? We're going to have a value, right? And we're going to say keep a value, right, if it does not equal key. Right, otherwise if it does, we're going to return, right, we're going to be in for each. So let's actually do for const n of neighbors, right, that way, else we can return false, right? This would mean we do have a cycle. We'd also have this kind of duplicated case here where if it doesn't have it, right, if it hasn't visited the key, right, that's, if we haven't visited this key before, that's great, right? But if we have, right, then we do still want to return false. So we could probably fuse these cases together, right, and then remove the simple cycle, prevent these simple cycles afterwards. And so let's see how this is working so far. And so we'll let r equals Actually, we can shorten this just by doing map.getN or map.set n's value equal to the map.get of n, right, dot filter, where v does not equal key. And we're saying map still, but we mean adjacency list. Doesn't have the visitor, we want to add it. All right, so we want to prevent simple cycles, so we go into 0, right? 0, we haven't visited before, so we add 0 to our visited set, right? And then we want to visit the neighbors. Well, we say, okay, if we haven't visited n before, then we're going to add n to the set. So we add 1, 2, and 3. But at the same time we add 1, we go adj.set n, which is 1. We get adj.n, which is going to be that array.filter the values, right, where v does not equal key, right? So this map should be updated with those values. So let's just print the adjacent. Let's just print the adjacency list after this operation, and we'll even print n to see what we changed, right? And we'll want to know what key was. So our map, right, our key is 0 and we're at n equals 3, right? And we're setting 3 to an empty array, which is perfect, right? And then we visit 1. Now we're saying we visited 1 already, so maybe we actually want to ignore the key to start. So we visit 1, 2, 3. And then right, so we visit the next one, we're guaranteed, right, if we keep adding key in, right, we're guaranteed to keep having this issue. So we do 1, 2, 3, right? Then when we visit 1, right, we're still going to have that problem, right? Actually, we would have that problem. We visit 1, 2, and 3. And so when we, right, so this iterative version is what we're seeing is that this iterative version just doesn't work. And we actually need to visit the node itself because we say we visit it, but we actually don't. And maybe we can do so, right? Maybe we can actually do so in this iterative version. We say const n of neighbors. If we say we're going to visit n, right, then we might as well add. So if we have const total n equals neighbors to start, right? If we haven't visited n before, right, because we'll have these neighbors, right? If we haven't visited n before, right, then we can actually add its children onto this list of neighbors to visit, right? And that would probably still be the same outcome, right? The problem would be that right now we're in our neighbors, so this needs to be done beforehand. So you'd have const n of neighbors if it has children, right, we're actually going to empty its children. And then additionally, right, we'd like to concatenate its children. So we'd say neighbors equal neighbors dot concat, right, add dot get and this new filtered version. All right, and we only want to actually visit a node, right, if its neighbors dot length is not equal 0. Right, and neighbors would be a constant, so we actually can't do that. So what we could do is actually do we'll do while total n dot length does not equal 0. Right. What we'll do is we'll say total n is equal to, and we want to change this to let equal to total n dot concat, right, add dot get to the neighbors of this n. Right, and this is actually gonna, and then what we can do, right, to get n, we'll say const n equals total n dot shift. So we'll just take it off the front, right? And so we'll visit 1, right? And we should filter out 0, right? And then we'll push 4, right? And then we'll visit 2, filter out 2, filter 3, filter out 3, right? And then we'll have 4, we'll visit 4. So we'll have filtered out 4 here. So I think this should make sense. Let's say concat argument of type number is not assignable to argument of type number. This is line 34. Argument of type number array. So total n. Oh, and we want this to actually be a spread, which I think is the problem. Then we concat. We should still be able to keep this concatenation the same. Zero, 1, 2, 3, 1 to 4. So 0, right, and we have 4, which is our n, and then we're actually going to filter out all nodes, right, and we actually, right, and this is the problem, we try to filter out 0, it's not 0 that we want to filter out, it's actually 1, and so our approach, this iterative approach of checking if there's a cycle is just convoluted. Let's try a simpler version, which can check if there's a cycle with a stack, right? So we can view our nodes. We'll do a recursive version, but an iterative depth first search, basically. right? And what we'll start with in the stack is actually going to be node 0, which is going to be this number, right? And what we're going to say is, right, while stack dot length does not equal 0, right? And we'll let cur equal to 0, right? Or cur does not equal -1. Actually, I think we can work with while stack length does not equal 0. Right, we'll have 0 to start, right? And we're going to want to visit 1 and 4. Right, so I'm going to say while cur does not equal, so I can't actually remember how to do the iterative, so let's just actually do depth first search style. So create a function called has cycle, right? And we'll pass in our adjacency list. We'll return false if it has a cycle, right? And then, so if has cycle, we're going to pass in the adjacency list, right? Visited, so we can visit each node once, and we're going to pass in our node to start, which presumably would be 0. And so up here, we can start to implement has cycle, which will have an adjacency list, right? Which will be a map of number to an array of numbers, right? And we'll have visited, which will be a set of numbers. And then we'll also have our the vertex that we're at, which will be a number, and we'll return a Boolean. Right, so if we've seen this node before, right, the vertex that we want to return false. Otherwise, we want to do visited dot add. We'll add the vertex, right? Since we're visiting this vertex, we're going to want to visit its neighbors, right? But we're going to want to remove the simple cycles first. So remove simple cycles, right? Then we'll visit the neighbors. Right, so how would we remove the simple cycles, right? So we have, right, for const n of map.getN, right? So these would be our neighbors. Right, now that we have our neighbors, what we'd like to do, and it's not a, we're going to want to change this to adjacency list. Right, we're going to have the neighbors that we're iterating over. So we're going to want to say, right, map.setN of the map.get, right? We want to get the neighbors for n, right? And so let's just say we're at 0, right? Our children, and we're at neighbor 1, right? So we're going to get the neighbor list for 1, right? And we're going to filter out, right, all values. We only want to keep values, right, that do not equal vertex. Right, and then from here, you can actually visit the neighbors, right? If we visit the neighbors, right, and none of them return false, then we want to return true, right? So what we'll do is we'll say if has cycle adjacency list, right, our vertex, which would be we want to pass in visited, right, with our vertex, right, and if it equals, if it has a cycle, right, then we're going to want to return true. And I'm realizing now our conditions are all over the place. If visited has vertex, then it does have a cycle, right, which we return true here. We want to return false, right, in the case where we visit all the neighbors and there's no cycle. So we have our adjacency. Let's check if this makes sense. If visited has vertex 0, we've never visited 0 before, so we'll add 0. We want to remove simple cycles. So for 1, 2, and 3, we're going to remove 0 from their lists. Then we're going to do the visit every node, right? We're going to say has cycle of adjacency list, right? Visited and n. So we're going to visit 1, right? Have we seen 1 before? No, so we add it to the vertex. We remove all these simple cycles, right? So we'd remove 1 from 4, right? Then we visit neighbors, right? But we actually have a neighbor of 1, which would be 4. So now we're at 4. Have we seen before? Have we seen 4 before? We haven't. So we want to remove the simple cycles for 4, but there won't be any. So we'll return false, right? And false again, right? So we'll be back at 0 with 2. We haven't seen 2 before and has no elements to traverse, right? So we return false. We haven't seen 3 before, so we add it, right? And we return there's no cycle here, so we should return false. So at line 8, what we mean is adjacency list again, and on line 8, blocks code variable n used before its declaration. Used before its declaration. So we'll just call this NEI for neighbor. Oh, I see what's happening. We can't use it for what we actually mean to check get is vertex, right? And we'll do the same here, const n of want to visit the neighbors again, and so this makes sense here. And so now we're able to tell if something has a cycle, but we should still fail because we're not checking for connectedness. So here we have no connectedness, and so this is where union find should come in. I'm wondering if we can actually tell connectedness in our map. And I think we could, if we try to visit every node right, we can actually check with visited.add vertex. If we know there's no cycle, right, then at the end, what we're also going to want to check, right, is if visited.size equals n. So if we visit every node, then it should be equivalent here. And so if we run it with this case, oh, so there we go. That's actually pretty cool. The other problem being that we actually didn't Get to use union find, which is fine. But additionally, the time complexity of this, I think, would be, so we have this has cycle function, right? We're checking if we have a cycle, right? Which is actually going to take linear time, and it takes linear time, right? Or it takes e time to set up all the edges in the map. So I think the time complexity would actually be e, right, where e is the number of edges, right, plus n, n is the number of nodes in the graph. Oh, right, so n plus e. So this is actually pretty cool. So graph theory plus iterative depth first search. We didn't do an iterative depth first search. Right, and it's really just if the stack is empty. We did a iterative depth first search. We didn't do iterative depth first search either, but we could to say, actually it would be the same space. How much graph do you know? There's a better definition for determining whether or not a graph is a tree. The graph to be a valid tree must have exactly n minus 1 edges. That's also a good point. For a graph to be a valid tree, it must have exactly n minus 1 edges. Any less, and it can't possibly be fully connected. Any more, and it has to contain cycles. Additionally, if the graph is fully connected and contains exactly n minus 1 edges, it can't possibly contain a cycle, therefore must be a tree. These facts are fairly straightforward to prove. I won't go into why they are true here, but if you're unfamiliar with these facts, I recommend reading up on graph theory. It's very important to be confident with graph theory in order to pass it. Going by this definition, our algorithm needs to do the following. Check whether or not there are n minus 1 edges. If there's not, then return false. Check whether or not the graph is fully connected. Check whether or not there are n minus 1 edges. All right, if there's not, then return false. Check whether or not the graph is fully connected. Turn true if it is. So actually, union find would be pretty cool here, since we'll know if there are any cycles if there are exactly n minus 1 edges. And then to check if it's fully connected, we could use union find. This is because undirected graph, we need to be careful of trivial cycles. Checking whether or not graph is fully connected is straightforward. We simply check if all the nodes are reachable from a search starting at a single node. Like before, we can check for connectivity using recursive depth first search, iterative depth first search, or iterative breadth first search. So we need to use scene set to prevent algorithm getting caught in an infinite loop if there are indeed cycles. So we have valid tree, blend edges, and if the length of edges does not equal n minus 1, then return false. Then we create an adjacency list. Still need a scene set to prevent our code from infinite looping if there is cycles. Wait. Right, n minus 1 actually lets us check if we're fully connected. So union find actually wouldn't help us there, because we can actually take that away and just check if edges.length is equal to n minus 1, which would probably give us the same time. Expected to return false. So we're checking if we have a cycle here, right? And if we don't, then our last check is if we're fully connected. Well, like they said, if edges.length is equal to n minus 1, oh, it does not equal. Well, if it does not equal n minus 1, then it's not a valid tree. Wait, no, maybe I'm misunderstanding. That doesn't make sense. if length of edges is not equal n minus 1, then return false. If you not this, and say if length of edges equals n minus 1, then return true.
Oh.
Maybe we want to turn the opposite. Well, this is the same as not using the ternary, so it's unclear what they mean by this. The length of edges n minus does not equal n minus 1, then return false. So maybe I'm misunderstanding. If we have the edges, it's actually much smaller with union find. So I'm not actually understanding why this doesn't return. Say if edges dot length not equal n minus, if edges dot length not equal n minus 1, then return false, right? And then if we make it down here, we'll just return true. Right, so this is just not the case. Right, input can be defined. So yeah, I see what they're getting at here, but it doesn't work. So if we want to know if the node, if it's fully connected, right, then every node we visited dot size should equal n. So that is interesting. For a graph, for the graph to be a valid tree, it must have exactly n minus 1 edges. Any less, and it can't possibly be fully connected. Any more, it has to contain cycles. Additionally, if the graph is fully connected and contains exactly n minus 1 edges, it can't possibly contain a cycle and therefore must be a tree. Definition simplify the problem, not checking whether or not the graph is fully connected. If it is, and if it contains n minus 1 edges, then we know it's a tree. Previous approach used. So presumably we do the same thing with union find by checking if all the root nodes are the same by loading them into a set. Or we could check, A, B, and edges. Interesting. Very, very interesting. So I would count that as a W. So we can just copy, go in here for our Explore card, paste it. And then we have number of connected components. We have 15 minutes for number of connected components. We have a graph of n nodes. You're given an integer n and an array edges, where edges sub I equals a sub I, b sub I indicates that there's an edge between a sub I and b sub I in the graph. Turn the number of connected components in the graph. The number of connected components. We're basically asking how many different root nodes there are, which could be answered, which is actually just like the number of provinces problem. This would be 1 since they're all indirectly connected to 1. This could actually be solved with union find. And so we'll create a class called quick union, where I don't have two properties, right? Root, which is going to store a direct correlation between our index in the array, which is going to be the vertice, and its parent node, and we're going to have rank, right, to do the quick union with optimization by rank. For a constructor, we're going to have the number of vertices, which is going to be a number, right? And for the vertices, what we're going to do is we're going to say for let I is equal to 0, right? I is less than num vertices. What we're going to do is the root in the quick union data structure, right, starts every value with its parent node as itself. So we'll do root dot push I, and we want to make this. We'll do this dot rank dot push 1 to start. Right, now we're going to have two more functions find, which is going to take a component x, which is a number, and it's going to return the root node for that value. In this version, right, we're going to take the root node, right, and not the parent node. And so we're going to let temp equals x, right, and we're going to say while temp, right, does not equal this dot root sub temp, right? So while we haven't found the root node, and the root node is the node in the root array where the index is the same as the parent, or the value in the index of the array, we're going to say x is equal to this dot root, not x, temp is equal to this dot root sub temp. And then we'll return temp once we get there. Then we're going to have our quick union function, which is going to be a union of component x and component y. And we're actually not going to return anything for this, but we could return if we actually created a union. Right, and the other thing we could also do to optimize this, we could have count, right, which will be equal to 0 to start, but we can set this dot count equal to num vertices, which will show how many vertices we have, right? But we can actually do the same thing. We can rename it, we'll call it roots, right? Because when we start, we have num vertices roots, right? And as we create unions, we decrease the number of roots. So we'll say is we'll get the root of x, which is going to be equal to this dot find of x, right? And then we're going to have root dot y, which is equal to this dot find of y, right? And if the roots are not the same, then we're actually going to do this dot roots minus equal 1, because we're now going to do a union, right? And if we're going to do a union, this is going to decrease the number of roots. Right, so the first one, to use the rank optimization from earlier, right, we're going to check if the rank of root x is greater than the rank of root y, which is basically just checking the height of the trees so far. We want to merge the tree at root y into the tree at root x. It's going to be dominated by the tree that already has the greatest height already. And so if that's the case, we'll say this dot root, we'll say this dot root of the root of root y, right? We're going to change it to the root x, right, to attach it. And then we're going to have the opposite of root y is greater than the rank of root x, right, then we're going to give root x, we're going to attach root x to root y, right? Otherwise, they're the same, right? And if they have the same root already, then we actually don't, actually, they're the same. Their roots are different, but in this case, their ranks are the same. So if their ranks are the same, right, we'll just say that root sub y will be given the root of root x. We'll increment the rank of root x. So now the problem, right, becomes creating this quick union data structure. We'll say new quick union with n, and we'll iterate over the const edge of edges, and we'll do qu dot union edge sub 0 and edge sub 1. Then we should be able to return qu dot count, which would be the number of, or qu dot roots, which should be the number of connected components, right? Or the number of components, or the number of components, right, that connect all the edges they've given to us. So we have start with 5, right, and we actually do the union of 0 and 1, right? So now we have 4, right? Then we do 1 and 2, right? Now we have 3, and then we do connect 3 and 4. Now we have 2 total connected components. That is oddly satisfying. Disjoint set. Imagine if a graph and vertices of 10 components will be n in that graph, and it's not at edge between 1 and 2, so we'll decrease the number of components by 1s because vertices 1 and 2 are now in the same component. We then add the edge from vertex 1 to vertex 2 to 3. Number of components will decrease by 1 again. However, this pattern will not continue when we add the edge from vertex 1 to vertex 3. Number of components will not change because vertices 1, 2, and 3 are already in the same component. Nice. So let's try. We have 7 minutes. Let's try the earliest moment when everyone became friends. There are n people in a social group labeled from 0 to n minus 1. We are given an array logs, where log sub I is equal to the timestamp of xi, yi that indicates that xi and yi will be friends at that timestamp I. Friendship is symmetric. That means if A is friends with B, then B is friends with A. Also, friend A is acquainted with person B if A is friends with B, or A is friend of someone acquainted with B. So we have indirect connections, basically transitive property. Return the earliest time for which everyone became acquainted with every other person. If there is no such earliest time, return -1. This looks like union find with extra steps, but I think we will stop there.